There is a size so small that the universe itself refuses to let you see it. 1 Planck length. Stack 1 billion atoms on top of each other. Now zoom into one of those atoms 1 billion more times. You still haven't reached it. And here's what makes this terrifying. Every time we try to look closer, we accidentally destroy what we're looking for. We'll travel from the birth of this idea in a German physicist's notebook, through boiling space, collapsing black holes, and pixels of reality. If you enjoy the journey, like and subscribe. We begin now. In 1899, a German physicist was trying to solve a problem about light bulbs. Max Planck had no idea he was about to stumble onto the smallest thing the universe allows. The problem he was working on sounds simple. When you heat metal, it glows. First red, then orange, then white. Scientists at the time had equations that described parts of this glow, but every equation broke down at some point. One formula worked for low-energy light. A different formula worked for high-energy light. Nobody could find a single equation that covered both. Planck called this the ultraviolet catastrophe, because the math predicted that hot objects should radiate infinite energy, which was obviously wrong. He spent months grinding through the numbers. Then, almost by accident, he found a fix. He assumed that light energy came in tiny fixed packets, instead of flowing in a smooth, continuous stream. He called these packets quanta. The math worked perfectly. Planck himself thought the trick was just a convenient shortcut, a mathematical band-aid. He assumed someone would eventually find the real explanation. Nobody did, because it turned out the packets were real, and buried inside his equations, almost as a side effect, was a set of numbers that described something even stranger. Planck realized that if you combined the speed of light, the gravitational constant, and his new quantum constant, you got a length. A specific, precise length that the universe seemed to care about deeply. He called it the Planck length, and he published it almost as a footnote. For decades, most physicists ignored it. It was so absurdly small that it seemed like a mathematical curiosity with no connection to real physics. To put the size in context, a single hydrogen atom is already almost unimaginably tiny. Now imagine shrinking that atom down until it is the size of the entire observable universe. The Planck length, sitting next to that shrunken atom, would be roughly the size of a standard bedroom. That's how far down we are talking. Planck spent the rest of his career working on quantum theory. He won the Nobel Prize in 1918. But he never fully accepted the wildest consequences of what he had started. He kept hoping that the physics would smooth out eventually, that the universe would turn out to be neat and continuous underneath. It didn't. The length he calculated in 1899 would later become the centre of the most disturbing unsolved problem in all of science. Here's what nobody tells you about that number. It showed up before anyone understood why it mattered. Planck found it using nothing but pure math and physical constants. No experiment. No telescope. No particle accelerator. Just equations pointing at a wall in the architecture of reality. Scientists spent most of the 20th century building tools powerful enough to approach that wall. Each time they got closer, something strange happened. The rules started breaking. The closer they pushed, the more the universe seemed to push back, and the reason it pushes back is something far weirder than anyone expected. Because looking at something small enough doesn't just require better tools. At a certain point, looking destroys the target. The very act of observation becomes the obstacle. Planck found the number in 1899. It took another century before physicists began to understand exactly why the universe chose that number as its limit. What happens when you try to cross that limit is where things get genuinely strange. Every comparison you've heard about the Planck length undersells it. Every single one. Scientists are used to dealing with small things. A human hair is about 1,000 times thinner than a millimetre. A red blood cell is about 10 times thinner than that hair. A virus is about 100 times smaller than that blood cell. A single atom is about 10,000 times smaller than a virus. and a proton packed inside the centre of that atom is about 100,000 times smaller than the atom itself. You might think we're getting close. We're nowhere close. The Planck length is roughly 100 million trillion times smaller than a proton. If that number doesn't land, try this. Take a proton and expand it until it's the size of the entire observable universe. The entire universe, every galaxy, every star, every speck of dust we can detect in any direction. Now, inside that expanded proton, the Planck length would be roughly the size of an average tree. That is the gap between where our best instruments currently operate and the floor of physical reality. Our most powerful particle accelerators, the machines we use to smash atoms apart and study what's inside, work at scales that are still millions of times too large to come anywhere close. We are not almost there. We are not even in the same conversation. And yet this number controls everything. Here's why the scale matters so much beyond just the shock of it. In physics, scale determines which rules apply. At the scale of planets and stars, gravity runs everything. At the scale of atoms and electrons, quantum mechanics takes over. At every scale in between, scientists have found equations that describe what they see. But the Planck length sits at the exact point where both sets of rules apply at the same time, and they completely contradict each other. That collision is what makes this size so special. Think of it like two gangs controlling different parts of a city. Gravity runs the large-scale neighbourhood, quantum mechanics runs the microscopic blocks. They've coexisted for over a century because they mostly stay in their own territory. The Planck length is the alley where both gangs show up at the same time, and the result is chaos that modern physics cannot currently describe. This was not something Planck could have predicted in 1899. He found the number. The meaning took decades to emerge, and the meaning, once physicists began to work it out in the mid-20th century, was unsettling. Because the Planck length isn't just small, it appears to be a boundary. A physical edge built into the universe itself. Every attempt to probe beyond it runs into the same set of problems, and those problems grow more severe the closer you get. Some scientists believe the Planck length reveals something fundamental about the structure of space itself. Others think it's a sign that our current math is broken. Both camps agree on one thing: something dramatic happens there. The next question is the one that opens the real mystery. If the Planck length is a wall, what is the wall made of? And why does the universe enforce it so ruthlessly? The answer starts with light, and with what light actually does when it tries to see something this small. To see anything, you need light. That's the foundation of every observation ever made. But light is strange. It behaves like a wave, and waves have a size. That size is called a wavelength. Visible light, the kind your eyes detect, has wavelengths roughly the width of a few hundred nanometers. That's why you can see a grain of sand but not a virus. The virus is smaller than the wave of light trying to illuminate it. The wave rolls right over it without registering a hit. To see smaller things, you need shorter wavelengths. This is exactly why scientists use X-rays to image bones and electron microscopes to see cells in detail. X-rays have shorter wavelengths than visible light. Electron microscopes use waves associated with electrons, which are shorter still. The pattern is consistent. Smaller wavelength equals finer detail. It works beautifully through scale after scale after scale, but there's a catch hiding inside this rule, and it becomes fatal at the Planck scale. Wavelength and energy are directly linked. Shorter wavelength means higher energy. A radio wave carries very little energy. A visible light wave carries more. An X-ray carries significantly more than that. A gamma ray, with an even shorter wavelength, carries enormous energy. Every time you want to see something smaller, you are required to throw more energy at it. At first, this seems manageable. Our particle accelerators work exactly this way. They fire particles at higher and higher energies to probe smaller and smaller structures. The Large Hadron Collider, the most powerful accelerator ever built, sends protons crashing together at energies that let physicists study details about 1,000 times smaller than a proton. This is genuinely impressive, and it is still millions of times too weak to reach the Planck scale. To actually resolve details at the Planck length, a particle accelerator would need to concentrate energy so extreme that it staggers imagination. A machine the size of the entire Milky Way galaxy, running at full power, might theoretically generate enough. Let that picture sit for a moment. A machine spanning 100,000 light years just to see one step below where our current tools go dark. But here's where the rule turns against itself completely. At the Planck scale, the energy required to form a short enough wavelength becomes so massive that something catastrophic happens before the observation can take place. That energy, packed into such a tiny point in space, reaches a threshold where it behaves like mass. And mass, in large enough concentrations in small enough spaces, does one thing: it collapses into a black hole. The tool you built to see something small enough destroys itself. The photon or particle you aimed at the target vanishes inside a micro black hole before it can bounce back to any detector. The measurement swallows itself. This is the exact point where the rule breaks. More energy no longer means more precision. Past a certain threshold, more energy means less information, because the information collapses before it can escape. The law that built every microscope, every particle accelerator, every imaging tool in human history turns against itself at the Planck length. And the reason it turns against itself is hiding inside the strangest partnership in science. What happens when gravity and quantum mechanics arrive at the same address at the same time is something nobody has fully solved. In a tunnel buried 300 feet underground, beneath the border between Switzerland and France, protons travel in circles at over 99% of the speed of light. The Large Hadron Collider is 17 miles around. It took 10 years and $10 billion to build. Thousands of scientists from over 100 countries worked on it. When it fires, the protons inside reach energies so extreme that for a fraction of a second after each collision, the conditions resemble what the universe looked like a billionth of a second after the Big Bang. It is the most powerful scientific instrument humans have ever created, and it still can't get anywhere close to the Planck scale. To understand the gap, picture a ruler. The Large Hadron Collider can measure down to about 1/10,000th the size of a proton. That's genuinely staggering. But the Planck length sits roughly 100 million trillion times smaller than that. Improving our best accelerator by any realistic engineering stretch wouldn't bridge that gap. Improving it 1,000,000 times over wouldn't bridge it. The numbers are so extreme that physicists don't even discuss reaching the Planck scale experimentally as a near-future goal. The conversation is about whether it's possible at all. To reach Planck energy using the same technology we currently use, you'd need an accelerator ring approximately the diameter of the Milky Way galaxy. 100,000 light-years of superconducting magnets and vacuum tunnels, built in open space, powered by an energy source that doesn't exist. Even if every engineering problem were solved, the structure would take thousands of years to build at any realistic speed. This isn't a funding problem, it's a physics problem. And here's the part that twists the situation further. Even if you somehow built that machine and somehow generated that energy and somehow aimed it correctly, the measurement would still fail, because at Planck energy, the concentration of energy in a point that's small triggers the same catastrophe every time. The laws of gravity take over. The probe collapses. The information disappears. The machine would not fail due to a flaw in engineering. The machine would fail because nature designed the outcome in advance. Some physicists find this deeply frustrating. They've spent careers building progressively more powerful accelerators, watching the horizon of knowledge expand with each machine upgrade, each new energy level reached. The Planck scale is the first horizon that doesn't move. Every tool you design to reach it runs into the same wall, at the same coordinates, for the same reasons. Other physicists find something almost beautiful in it. The universe is telling us something. The fact that observation itself breaks at a precise and calculable length suggests that the Planck length isn't an accident, it's a built-in feature. A design choice, if you're willing to use that word loosely. What's certain is that the limit exists, and the reason it exists is written into the relationship between energy and gravity. That relationship has a name. It comes from Albert Einstein's work in 1915, and it describes the exact mechanism that makes Planck's scale observation physically impossible. The mechanism is simple to describe and staggering to accept. Albert Einstein published his theory of general relativity in 1915. He described gravity as a geometry problem. Mass bends space. The bigger the mass, the sharper the bend. Earth bends space gently enough that you can walk around on its surface. The Sun bends it strongly enough to keep 8 planets in orbit. A neutron star bends it so severely that atoms on its surface get crushed flat. A black hole bends it so completely that nothing, not even light, can climb back out. Einstein's equations connected mass, energy, and the shape of space in a single framework. One of the most famous results was the formula that says mass and energy are 2 forms of the same thing. You can convert between them. A tiny bit of mass equals an enormous amount of energy. That's the idea behind nuclear reactions. But the relationship works in both directions. Energy also behaves like mass. Concentrate enough energy in a small enough space, and that energy starts bending space exactly the way a massive object would. This is the key that unlocks the Planck wall. When physicists try to measure something at the Planck scale, they need a photon or a particle with enormous energy. That energy, focused into a region the size of a Planck length, is so dense that Einstein's equations activate. The space around that concentrated energy begins to curve. It curves faster than any instrument can react. And at a precise threshold, defined by a number called the Schwarzschild radius, the curvature becomes total. The space closes around the energy. A black hole forms. The Schwarzschild radius is the point of no return for any mass or energy. Pack any amount of mass into a sphere smaller than its Schwarzschild radius, and that sphere becomes a black hole. For the Sun, the Schwarzschild radius is about 2 miles. Compress the Sun into a ball 2 miles across, and gravity takes over completely. For the energy needed to probe the Planck scale, the Schwarzschild radius is exactly 1 Planck length. This is the moment where the coincidence stops being a coincidence. The minimum length quantum mechanics says you need to probe is the Planck length. The Schwarzschild radius for the energy required to do that probing is also the Planck length. Both numbers arrive at the same address. The 2 most powerful theories in physics converge on a single forbidden zone and agree, for once, on exactly where the boundary sits. One theory says you need this much energy to see this small. The other theory says that much energy in that smaller space creates a black hole. The result is a perfect trap. Every attempt to look collapses into itself before the information escapes. Einstein spent the last 30 years of his life searching for a unified theory that would bridge quantum mechanics and gravity. He failed. Every physicist who followed him has also failed. And the Planck length is the exact coordinate where that failure becomes most visible. What happens inside that black hole, that tiny collapsing point of failed measurement, is the next layer of the mystery. Every black hole in the universe has a point of no return. Cross it, and nothing comes back. Astronomers call this boundary the event horizon. Carl Schwarzschild calculated the math for it in 1916 while serving on the Russian front in World War I. He sent his equations to Einstein from the battlefield. Einstein reportedly said the calculation was the most elegant thing he had seen. Schwarzschild died of an illness at the front just months later. His equations survived. The Schwarzschild radius is simple in concept. Take any mass, calculate how small you'd need to crush it before gravity becomes overwhelming and unstoppable. That radius is the Schwarzschild radius. For a mountain, it's about 1/1,000,000th of an inch. For the Earth, it's about the size of a marble. For the Sun, it's roughly 2 miles. These numbers are academic as long as nothing actually compresses matter that far. Mountains and planets don't spontaneously crush themselves. But energy behaves the same way mass does in Einstein's equations, and this is where things get dangerous at the Planck scale. Every measurement probe, whether a photon of light or a particle fired from an accelerator, carries energy. The more precisely you want to locate something, the more energy your probe needs. As the target shrinks toward the Planck length, the required energy climbs so steeply that at exactly 1 Planck length, the probe's energy reaches its own Schwarzschild threshold. The probe becomes a black hole. Instantly, a micro black hole at this scale evaporates almost immediately. Physicist Stephen Hawking showed in 1974 that black holes slowly radiate energy and shrink. At the tiny masses involved here, the evaporation is nearly instant. The black hole flashes into existence and vanishes in a time so short it makes a billionth of a second look leisurely. But during that flash, the measurement information disappears. The probe never bounces back. No detector ever receives a signal. Here's the part that keeps physicists up at night. You could make your probe more powerful, trying to force the measurement through. But more powerful means more energy. More energy means a bigger Schwarzschild radius. A bigger radius means a larger black hole. A larger black hole takes longer to evaporate and swallows more information before it does. The harder you push, the more violently the universe erases your data. You cannot outrun this. You cannot engineer around it. The scaling works against you with mathematical precision. Every additional unit of energy you throw at the problem makes the problem worse by the same proportion. Schwarzschild found his equation to describe a phenomenon he expected to remain purely theoretical. He probably never imagined that the same math would one day describe the fundamental barrier to all physical measurement. His battlefield calculation became the architecture of a wall that sits at the bottom of reality itself. And yet the Schwarzschild radius only explains half the barrier. The other half comes from a different direction entirely. It comes from the quantum side of physics, from the rules governing uncertainty itself, and from a physicist who discovered those rules in a very different context. His name was Werner Heisenberg, and his discovery adds a second lock to the same door. Werner Heisenberg was 25 years old when he wrote one of the most unsettling papers in the history of science. Published in 1927, his uncertainty principle said something that sounded impossible at first. You can never know both the exact position and the exact speed of a particle at the same time. The more precisely you pin down where something is, the less precisely you can know how fast it's moving. Measure one perfectly, and the other becomes completely unknown. This wasn't about bad instruments. Physicists first assumed it was a practical problem. Build better tools, and the uncertainty goes away. Heisenberg showed that the uncertainty was written into the structure of reality. The particle doesn't have both a precise position and a precise speed simultaneously. Both values genuinely don't exist at the same time. The reason connects back to the measurement problem. Observing a particle changes it. To locate a particle precisely, you fire a photon at it. That photon transfers energy to the particle when it hits, knocking the particle sideways. The shorter the wavelength of the photon, the more precisely it pins down the particle's location. But a shorter wavelength means higher energy, and higher energy means a harder knock, meaning the particle's speed becomes more uncertain after the hit. You cannot avoid this trade-off. It's baked into the relationship between wavelength and energy. Now apply this to the Planck scale. To locate a particle within 1 Planck length, you need a photon with a wavelength that short. That photon carries the energy needed to collapse into a micro black hole, as covered before. But even setting aside the black hole problem, Heisenberg's principle adds a separate constraint. The more precisely you pin down a particle's position, the more wildly uncertain its momentum becomes. At the Planck scale, the uncertainty and momentum becomes so large that the particle could be moving at nearly the speed of light in any direction. It essentially disappears from the place you just found it before any measurement can be recorded. Both traps operate simultaneously. Einstein's gravity collapses the probe into a black hole. Heisenberg's uncertainty scrambles the target's position before the data arrives. The particle you're trying to measure is simultaneously inside an event horizon and occupying an undefined location. Information fails twice, from two independent directions, governed by two completely separate sets of rules. What makes this especially haunting is that Heisenberg derived his principle from quantum mechanics alone. He wasn't thinking about gravity or black holes or Planck lengths. He was working out the logical consequences of wave-particle duality. The fact that his completely independent derivation hits a wall at the exact same length as Einstein's completely independent calculations is either a profound clue about the structure of the universe or the most striking coincidence in the history of physics. Scientists who study this problem lean heavily toward the former. The agreement feels like both theories are pointing at the same underlying truth, a truth that neither theory can fully describe yet. That truth lives at the Planck scale, and the closer you look at it, the more it looks like it's looking back. What happens to space itself when these two sets of rules collide will shatter any remaining sense that the universe is built on solid ground. Every particle in the universe has a blur zone, a region where its position becomes fundamentally smeared no matter what you do. This blur zone has a name: the Compton wavelength. It was named after American physicist Arthur Compton, who won the Nobel Prize in 1927 for showing that light behaves like a particle when it bounces off electrons. His work was one of the foundational proofs of quantum mechanics, but buried in the math he developed was a specific length tied to each particle's mass. Here's what the Compton wavelength actually means. If you try to localize a particle to a region smaller than its Compton wavelength, you pump so much energy into the measurement that you spontaneously create new particles out of that energy. This isn't a side effect or an accident. It's what energy does at this scale. Einstein showed that mass and energy are interchangeable, and quantum mechanics shows that concentrated energy produces particles. Compress the measurement zone past the Compton wavelength, and the particle you're trying to study gets buried under a cascade of new particles that the measurement itself just manufactured. You started trying to find one particle. The act of looking created dozens. Now you can't tell which one you were originally studying. For an electron, the Compton wavelength is roughly 2/trillionths of an inch. For a proton, it's even smaller. These are already far beyond what the naked eye can detect. But the Planck length sits astronomically further down. Here's where it gets strange. At the Planck scale, the Compton wavelength and the Schwarzschild radius arrive at exactly the same number. The blur zone from quantum mechanics and the point of no return from gravity converge at one Planck length. Two entirely different physical laws, built from different mathematics, describing different phenomena, point at the same coordinate. Think of it like two separate treasure maps, drawn by different people in different centuries using different languages. When you follow both sets of directions, you arrive at the exact same spot. The Compton wavelength sets the quantum limit, go smaller than this and new particles erupt. The Schwarzschild radius sets the gravitational limit, concentrate this much energy, and a black hole forms. At the Planck length, both thresholds activate at once. A measurement that's small would simultaneously trigger particle creation and gravitational collapse. The particle you wanted to study would drown in a flood of newly created particles, while the entire local region of space collapsed into a black hole. The information doesn't just become hard to read, it becomes physically impossible to recover. What's striking is that Compton, Heisenberg and Einstein each developed their ideas independently, working on different problems in different decades. None of them set out to find a fundamental limit to measurement. Yet each of their frameworks arrives at the same wall. 3 separate roads, 3 separate starting points, one destination, The Planck length keeps appearing wherever physicists push their equations to the edge. It's in the entropy of black holes, it's in the math of quantum gravity, it's in the structure of string theory and loop quantum gravity. Every time physics tries to describe the extremely small, the Planck length shows up like a stop sign, buried in the equations. And what the universe is doing behind that stop sign is the strangest idea in all of physics. For over 100 years, physics has been running on two operating systems that refuse to speak to each other. General relativity describes the large-scale universe with extraordinary precision. The curves of space-time, the orbits of planets, the bending of light around massive objects, the expansion of the universe itself. Every prediction general relativity makes has been confirmed. The GPS satellites circling Earth right now have to apply corrections calculated from Einstein's equations, or your phone's navigation would drift by miles every day. The theory works. Quantum mechanics describes the small-scale universe with equally stunning accuracy. The behavior of electrons, the structure of atoms, the way light interacts with matter, the forces that hold atomic nuclei together. The predictions of quantum mechanics match experiments to over 10 decimal places. Some physicists call it the most precisely tested theory in human history. It works. The problem is that they work in completely different ways. General relativity describes a smooth, continuous universe. Space and time are a fabric, and that fabric curves gracefully in response to mass and energy. Everything in the theory is precise, deterministic, and geometrically elegant. If you know the starting conditions, you can calculate the outcome exactly. Quantum mechanics describes a fundamentally uncertain universe. Particles don't have exact positions or speeds. Energy comes in discrete jumps. Outcomes are probabilistic, not certain. The fabric of reality at small scales is grainy and blurry, defined by probability clouds rather than sharp lines. At the scales where each theory operates, the other one can be safely ignored. Gravity is too weak to matter in atomic calculations. Quantum effects average out and become invisible at the scale of planets. Both theories are accurate within their territory because they never have to deal with each other. The Planck scale ends that arrangement. At one Planck length, both theories become relevant simultaneously. You can't ignore gravity because the energy involved curves space-time severely. You can't ignore quantum mechanics because you're dealing with scales where quantum uncertainty dominates. Both sets of equations must apply at once. And when you try to run both at once, the math breaks. Combining the two produces answers that include infinities. In physics, infinity as an answer usually means the theory is missing something. It means you've pushed the equation past its valid range. When quantum mechanics and general relativity are forced to overlap at the Planck scale, the infinities multiply, the equations generate nonsense, the mathematics collapses before you can extract any meaningful answer. This failure has a name. Physicists call it the problem of quantum gravity. It's considered the single greatest unsolved problem in modern physics. Solving it would require a new framework that contains both general relativity and quantum mechanics as special cases, the way both theories themselves contain classical Newtonian physics as a special case. No one has found that framework yet. And the Planck length sits at the exact coordinates where the absence of that framework becomes physically catastrophic. Every experiment, every calculation, every observation that tries to bridge the gap hits the same mathematical wall. The universe, it seems, is protecting that wall with everything it has, including one of the strangest phenomena any physicist has ever imagined. John Archibald Wheeler was one of the most creative physicists of the 20th century. He worked on the Manhattan Project. He collaborated with Einstein and with Niels Bohr. He gave black holes their name, and in 1955 he proposed something that made even his colleagues uncomfortable, that space itself, at the Planck scale, is boiling. Wheeler had been thinking carefully about what Heisenberg's uncertainty principle implies when applied to space rather than particles. The uncertainty principle says energy has a blur zone. You cannot know the exact energy of a region of space at any exact moment in time. The more precisely you try to define the time, the more uncertain the energy becomes. These fluctuations are tiny and average out at the scales we experience, but at the Planck scale, they become violent. At 1 Planck length, the energy fluctuations become so extreme that they are comparable to the energy needed to form a black hole. The fabric of space cannot remain flat or smooth under these fluctuations. It twists. It buckles. Tiny black holes and wormholes spontaneously form and evaporate faster than any instrument could ever detect. The geometry of space itself becomes unpredictable, constantly tearing open and stitching back together in random configurations. Wheeler called this quantum foam. Picture the surface of a calm ocean seen from far above. From 10,000 feet up, it looks flat and smooth, but drop down to the surface and you see waves. Drop to an inch above the water in a storm, and the surface is violent, chaotic, nothing like the smooth plane it appeared from altitude. The Planck scale is the storm surface of space itself, seen from the closest possible distance. At this scale, space and time lose the properties we rely on to define them. There is no straight line, because the geometry keeps changing. There is no fixed distance, because the space between 2 points fluctuates by a Planck length every Planck unit of time. There is no stable geometry that a measurement could anchor to. This is why the question of what the Planck length is measuring becomes strange. We think of length as the distance between 2 points, but at the Planck scale, the concept of between breaks down. The 2 points are connected by a space that foams and shifts and collapses and regenerates constantly. The ruler doesn't stay straight long enough to give a reading. Wheeler's quantum foam was a theoretical proposal. Scientists have not directly observed it, because for the reasons already discussed. Direct observation at that scale is physically impossible. But the idea fits consistently with everything quantum mechanics and general relativity predict about the behavior of space at extreme scales. Several experimental groups have looked for indirect signs of quantum foam by studying how light from distant galaxies travels across the universe. Some results have hinted at small irregularities that could be consistent with a foamy spacetime. Others have seen nothing. The question remains open. What isn't in question is the underlying logic. At the Planck scale, the energy fluctuations are real, the geometry must respond to them, and the smooth space we live in every day is a large-scale average of something far more turbulent underneath. That turbulence hides something even stranger inside it. Inside the boiling quantum foam, something even more extreme happens. Wormholes form and die before they can be measured. A wormhole in general relativity is a tunnel through spacetime. Einstein's equations allow for them mathematically. They connect 2 separate regions of space through a shortcut, bending the fabric of spacetime until 2 distant points touch. In science fiction, they're used for instant travel across the galaxy. In reality, they've never been observed. Creating a stable wormhole would require a type of exotic matter with negative energy, and nothing like that has ever been confirmed to exist. Most physicists consider traversable wormholes somewhere between extremely speculative and impossible. At the Planck scale, though, the math changes. Wheeler's quantum foam model predicts that wormholes form spontaneously at this depth. The energy fluctuations that create quantum foam are violent enough to temporarily punch holes in the fabric of spacetime. These holes connect 2 nearby points through a brief tunnel before immediately closing. Immediately is not a strong enough word. The entire existence of one of these wormholes lasts 1 Planck unit of time. That is the time it takes light to cross 1 Planck length. It measures roughly 10 million trillion seconds. Compared to that duration, the shortest event we've ever directly measured in a laboratory is an eternity. These wormholes are so small that a single electron couldn't squeeze through them. They're so short-lived that no information could traverse them and escape before they close. They exist in a regime so far below the resolution of any possible detector that the only evidence for them is the mathematical framework that predicts they must exist. But here's what makes this idea compelling rather than dismissible. The quantum field theories that describe particle physics already depend on something similar in a gentler way. Particles constantly borrow energy from empty space and pay it back so quickly that it doesn't violate any conservation laws. These are called virtual particles, and they have measurable effects on real experiments. The Casimir effect, a measurable force between two closely spaced metal plates in a vacuum, exists specifically because of virtual particle activity in the space between them. Planck-scale wormholes are an extreme version of the same underlying logic. Space at its deepest level is not empty, not static, and not stable. What this means for the concept of emptiness is difficult to process. The vacuum of space, the nothing between stars and galaxies, is actually a seething structure at scales too small to see. The farther down you go, the more activity there is. The empty regions of the universe, at the Planck level, are the most eventful places in existence. The word empty stops meaning anything. And this realization leads to one of the most radical proposals in modern physics. A proposal that says the smooth, continuous space we move through every day may be an illusion. That what looks like open road is actually a mosaic, and each tile in that mosaic is exactly one Planck length across. Every photograph you've ever seen on a screen is built from pixels. Zoom in far enough and the sharp image breaks down into a grid of coloured squares. The image looks smooth from a normal distance because your eyes can't resolve the individual tiles. But the continuous surface is an illusion. Underneath it is always a grid. Some physicists believe space works the same way. The idea is called the pixelated universe, or sometimes discrete spacetime. The proposal is that space is not infinitely divisible. You cannot cut a length in half forever, approaching zero without limit. At the Planck length, you hit the smallest tile. There is nothing smaller because there is no physical structure below that scale to accommodate a smaller measurement. The difference between space and a photograph is that the photograph's pixels are just an engineering choice. A higher resolution screen has smaller pixels. There's no fundamental law requiring a particular grid size. The Planck length, if this idea is correct, is a fundamental law, a universal grid enforced by the structure of reality itself. Here's an analogy that helps make this concrete. Imagine a chessboard. A piece can be on square A1 or square B1. There is no square halfway between them. The board's architecture doesn't support a half-square position. The Planck length may function as the chessboard's minimum square size for the universe. You can move to neighbouring Planck-sized regions. You cannot move to a position half a Planck length from where you started, because that position has no physical existence. This would have staggering implications for mathematics and physics. Calculus, the mathematical tool that underlies almost all of modern physics, is built on the assumption that space and time can be divided infinitely finely. Integrals sweep over continuous ranges. Derivatives describe instantaneous rates of change. The entire framework presupposes that between any 2 points there are infinitely many points in between. If space is discrete at the Planck scale, calculus is an approximation, not an exact description of reality. A very good approximation at large scales, but fundamentally imprecise at the bottom. This is the same relationship that exists between a smooth-looking digital photo and the pixel grid beneath it. At normal resolution, calculus describes physics beautifully. At Planck resolution, something else must take over. What that something else might look like is the central challenge for physicists working on quantum gravity. The math of a discrete spacetime requires different tools, and those tools haven't been fully developed yet. Researchers in loop quantum gravity have made the most systematic attempt to build them, and they're producing results that are suggestive, but not yet fully confirmed. What's already clear from multiple independent directions in physics is that the assumption of infinite divisibility breaks down at the Planck length. Whether space is discrete in a literal pixel grid sense, or simply unmeasurable below this scale for other reasons, the result is effectively the same. The universe refuses to be subdivided past a specific minimum. Infinity, it turns out, stops somewhere. But if space has a minimum size, something even more unsettling follows. Time, which is woven together with space into a single fabric called space-time, might have a minimum size too. Space and time are not separate things. Einstein showed that they form a single fabric called space-time, and nothing in that fabric affects one without affecting the other. So if space has a minimum length, the Planck length, then time must have a minimum duration. And it does. It's called Planck time. Planck time is the duration it takes light to cross one Planck length. Since the Planck length is the smallest possible distance and light travels at a fixed speed, the Planck time is the smallest possible interval of time. Events that happen faster than one Planck time cannot be separately distinguished. They collapse into a single, unresolvable moment. To feel the scale of this, 1 second contains roughly 10 million trillion Planck time units. Written out, that number would stretch across more pages than there are atoms in the solar system. The most powerful scientific instruments we have can detect events lasting a billionth of a second, which still sits enormously far above the Planck time threshold. The implications run deep. Cause and effect, the foundation of all scientific reasoning, depends on time having a sequence. Event A happens, then event B happens, and we can say A caused B because A came first. But at the Planck time scale, the concept of first and second breaks down. If two events happen within 1 Planck time of each other, there is no physical way to determine which came first. Their sequence becomes undefined. Causality, the bedrock principle that makes experiments possible, dissolves. This is the point where physics runs out of language. Every experiment ever performed, every measurement ever taken, every causal chain ever documented in human history has assumed that time moves forward in a defined sequence. At the Planck scale, that assumption fails. The concept of before and after is a large-scale feature of the universe, the same way smoothness is a large-scale feature of the photograph's pixel grid. Below 1 Planck time, reality doesn't have a sequence. There's an even stranger implication hiding here. If time has a minimum tick, then motion itself becomes quantized. Continuous motion through space means passing through every point along a path. Quantized motion means jumping from one Planck-sized location to another without occupying any position in between. Like a game character that appears in one square, then the next, without smoothly crossing the space between them. This has not been confirmed experimentally, but it follows logically from the combination of discrete space and discrete time, and several theoretical frameworks predict it. The universe we experience, with its smooth flowing motion and continuous ticking of time, looks the way it does because we're looking at an average of enormous numbers of Planck scale jumps. Just as a film creates the illusion of smooth motion from a sequence of still frames, space-time may create the illusion of continuity from a sequence of discrete steps. Each step is exactly 1 Planck length. Each frame lasts exactly 1 Planck time, and the projector, whatever is running the film, remains completely out of reach. Understanding what that projector might be requires diving into two of the most ambitious and competing theories in physics. Both were built to answer the same question. They arrived at very different answers, and neither has been proven right yet. Here is a thought experiment that makes the breakdown of causality feel real. Two events happen at opposite ends of a Planck length gap from each other. The gap is so small that even light cannot cross it in less than 1 Planck time. You want to determine whether event A caused event B, or whether event B caused event A. To answer that question, you need to know which came first. You fire a probe to investigate, but the probe cannot be located to within 1 Planck length without triggering the collapse problems already described. The measurement fails. You try a different approach. You track the energy signals from both events. But energy signals travel no faster than light, and at this scale, the travel time across 1 Planck length is 1 Planck time, which is the smallest defined interval. The signals arrive simultaneously from your detector's perspective, because the time gap between them cannot be resolved. You have no way to determine sequence. You cannot assign cause to either event. The relationship between them is undefined by physics. This is a genuine crisis for the scientific method, which assumes that the physical world has a defined causal structure everywhere, not just at scales we can observe. The assumption runs so deep that most people never notice it. Every measurement you take assumes that the signal from the thing you measured travelled to your detector after the event occurred. That time ordered that experience correctly. That the reading on your instrument reflects a past event and predicts future ones. These assumptions are woven into the structure of experiment itself. At the Planck scale, they fail. The universe at this depth doesn't have a defined time direction. The quantum foam isn't just spatially chaotic, it's temporally chaotic. Time at the Planck scale doesn't flow in a single direction. It doesn't flow at all in any recognizable sense. It fluctuates and loops and becomes ambiguous in ways that make the arrow of time, the sense that past and future are different directions, disappear entirely. Physicists talk about this as the problem of time in quantum gravity. It's one of the deepest conceptual challenges in the field. General relativity allows time to be stretched and warped by gravity, but it still flows forward. Quantum mechanics has its own time issues, since its equations are mostly reversible and the direction of time has to be added in by hand. At the Planck scale, both sets of issues combine and the whole notion of temporal order collapses. Some theorists have proposed that time itself is emergent. Like temperature is not a fundamental property of matter, but something that emerges from the average behaviour of billions of moving molecules, time may emerge from the collective behaviour of something more fundamental at the Planck scale. In this view, before and after are concepts that only come into existence when enough Planck scale building blocks are assembled into a large-scale structure. Below that threshold, the universe has no clock. It has no sequence. It has no story. And that creates the deepest problem of all. If space and time both become undefined at the Planck length, then the very stage on which all physics happens disappears. You're left with a gap in the architecture of reality that no current theory can fill. Two theories have tried. Both are impressive. Both are incomplete. And their rivalry is one of the great unresolved battles in science. Every science ever practiced by humans rests on one foundational act: measurement. You observe something. You record it. You compare it to a standard. You build models that predict future observations. You test those models against new measurements. The cycle never ends. It's the engine of all scientific knowledge. Measurement requires a few things that seem obvious until the Planck scale takes them away. It requires that the thing being measured exists in a defined state. It requires that a probe can interact with the thing and carry information back. It requires that space and time between the probe and the detector are stable enough for the signal to propagate. It requires that the act of measuring doesn't catastrophically destroy the information being sought. The Planck length violates all four simultaneously. Below this scale, things don't have defined states because quantum uncertainty makes their positions and energies fundamentally indeterminate. No probe can interact with a target and return information because the probe collapses into a black hole before it can escape. Space and time become so turbulent in the quantum foam that a signal has no stable medium to travel through, and every attempt to extract information from this scale destroys more than it reveals. The Planck length is a hard wall, not a temporary wall that better technology will someday breach. A wall written into the laws of physics themselves. This is the moment where a scientific civilization hits its absolute horizon. Every other frontier in science is a matter of building bigger telescopes, faster computers, more sensitive detectors, or cleverer experiments. The Planck scale is different. There is no upgrade path. There is no clever experimental design that sidesteps the fundamental limits of measurement. The wall exists because of what measurement itself is, which is a physical interaction, and physical interactions at this scale destroy their own data. Some scientists find this deeply troubling. The scientific method assumes in principle that any question about the physical world can eventually be answered through observation and experiment. The Planck scale is the first case where the universe enforces a permanent exception. Certain truths about the fundamental architecture of reality appear to be locked away not by practicality but by physical law. Others find it clarifying. The existence of a physical horizon tells scientists something important. It tells them the Planck scale isn't just a scale at which things get harder to measure. It's a scale at which the current framework of physics breaks down entirely. That breakdown is a signal pointing toward a deeper theory that lies beyond the reach of current mathematics. The wall is not the end of the story. It's a sign that there's more story on the other side. Reaching that story requires abandoning some of the most basic assumptions physicists have worked with for centuries. It requires imagining physics in a world where space has no smooth geometry, where time has no definite direction, where distance is not a number you can always calculate. Two theoretical frameworks have tried to build that new physics. They differ on almost every major point, but both take the Planck length as their starting gun. The first framework says everything we know about particles is wrong. String theory starts with a radical claim. Every particle you've ever heard of, every electron, every quark, every photon, every building block of matter and light, is made of the same thing, a tiny vibrating loop of energy. These loops are strings. They're not made of anything smaller, they're the bottom floor. And every different particle in existence is the same type of string vibrating in a different pattern. An electron is one vibration frequency. A quark is another. A photon is another. The differences between all the particles in the universe reduced to differences in how an underlying string shakes. The strings have a size. They're roughly 1 Planck length across. This is not a coincidence. The theory requires this size because, at the Planck scale, the string's vibrations begin to interact with the curvature of spacetime in ways that automatically include gravity. By building the Planck length into the size of the fundamental unit, string theory forces gravity and quantum mechanics to coexist in the same mathematical framework. This is the theory's greatest appeal. It's the only framework physicists have found where quantum mechanics and gravity emerge from the same starting point, without generating the catastrophic infinities that appear when you try to combine them by force. The theory also requires extra dimensions. The strings don't vibrate in the 3 spatial dimensions we can observe. They require additional hidden dimensions, curled up so tightly that they're invisible at any scale we can currently probe. Different versions of the theory require different numbers of extra dimensions, ranging from 6 to 7 extra dimensions, making the total either 9 or 10 spatial dimensions plus time. The extra dimensions are curled at the Planck scale. Every dimension beyond the 3 we see is folded up into a space roughly 1 Planck length across. So even if they exist, we have no way to enter them, detect them directly, or rule them out experimentally, because we can't access the Planck scale. This is string theory's central problem. It elegantly resolves the clash between quantum mechanics and gravity. It produces a consistent mathematical framework with no infinities. It predicts results that are internally coherent. But it predicts them at the Planck scale, which is permanently inaccessible to experiment with any foreseeable technology. After decades of development, string theory has produced no confirmed experimental predictions that differ from the existing theories it was meant to replace. Physicists debate fiercely whether it's on the right track. Some argue that the mathematical consistency of the theory is itself evidence of its truth. Others argue that a theory with no testable predictions isn't physics, it's mathematics. The debate is ongoing. String theory's competitor in the race to describe the Planck scale takes a completely different approach, and it makes a claim that seems even stranger on first hearing. It says space isn't made of dimensions at all. Loop quantum gravity begins with a different question than string theory. String theory asks what particles are made of. Loop quantum gravity asks what space itself is made of. The answer it proposes is this: space is a network. A web of interconnected loops, woven together into a fabric. Each loop is roughly 1 Planck length in size. Each connection between loops is a quantum of space, an irreducible unit. The smooth space we experience is what this network looks like at large scales, the same way a woven fabric looks smooth from across the room, even though up close it's made of individual threads. The theory was developed in the late 1980s and 1990s by several researchers, most prominently Abhay Ashtekar, Lee Smolin, and Carlo Rovelli. It grew from a direct attempt to apply quantum mechanics to Einstein's equations of general relativity without adding any extra dimensions or new types of particles. The result was a picture where space is fundamentally granular. Granular means made of grains. Individual, irreducible chunks. At the Planck scale, the network is visible and each node is distinct. At the scales of everyday life, there are so many nodes in any region of space that the graininess disappears into apparent smoothness, the same way a sandy beach looks smooth from altitude. Loop quantum gravity makes a specific mathematical claim about the minimum possible volume of space. There is a definite smallest chunk, a single quantum of three-dimensional space, and its volume is on the order of 1 Planck length cubed. Space cannot be subdivided past this point because the mathematical structure of the theory rules out smaller configurations. The loops simply cannot be arranged into a smaller volume. This means the pixelated universe is literal in loop quantum gravity. Space has a minimum pixel, and the Planck length sets its size. Time in loop quantum gravity is also discrete. Change happens in minimum steps, each 1 Planck time. Between those steps, in the strict mathematical sense, nothing happens. Time is a sequence of discrete moments, each separated by the minimum tick. Loop quantum gravity has produced several results that connect to observable physics. It resolves the singularity at the centre of a black hole, replacing the point of infinite density with a quantum bounce. It predicts that the Big Bang may have been preceded by a collapsing previous universe that bounced back. These predictions are testable in principle through detailed observations of the cosmic microwave background radiation that fills the universe as a remnant of the Big Bang. Experiments analysing that radiation have begun to produce data that some researchers claim is consistent with loop quantum gravity's predictions. Others argue the signals are too faint to conclude anything definitive. Both string theory and loop quantum gravity agree on one point: the Planck length marks the edge of the known. Beyond it lies the foundation of physical reality, waiting to be understood. And that foundation, if either theory is on the right track, is stranger than anything physics has described before. What lies on the other side of the Planck wall may be the deepest question the human mind has ever tried to answer. 2 camps. One question. No confirmed answer. On one side, string theorists. On the other, loop quantum gravity researchers. Both groups contain brilliant physicists. Both frameworks have produced elegant mathematics. Both claim to describe what happens at the Planck scale, and after decades of work, neither side has produced a single confirmed experimental result that distinguishes their theory from everything else. This isn't a minor academic disagreement, it's a fundamental split about what reality is made of at its deepest level. String theorists believe that the extra dimensions required by their theory are real, but hidden, curled up at the Planck scale. They believe that all particles are vibrations of the same underlying string, and that gravity is just another vibration mode in the same family. They've built a mathematically rich framework called M-theory that unifies different versions of string theory into a single structure. The math is impressive enough that many string theorists treat it as compelling evidence on its own. Loop quantum gravity researchers reject extra dimensions entirely. They take the 3 dimensions of space and 1 of time as fundamental, and they apply quantum mechanics directly to Einstein's equations without adding anything new. They argue that string theory's elegance comes at the cost of predictions, that a theory with no falsifiable outputs in the foreseeable future isn't science in the traditional sense. String theorists fire back that loop quantum gravity struggles to recover the smooth relativistic spacetime of everyday experience from its discrete loop structure. proving that a network of Planck-scale loops reproduces Einstein's smooth curved spacetime at large scales has proven technically difficult. Both criticisms carry real weight. Some physicists have stepped back from both camps and proposed that the answer lies somewhere neither theory has fully explored yet. They argue that both string theory and loop quantum gravity are approximations of a deeper structure, the same way Newton's gravity is an approximation of Einstein's, valid in a limited range but missing something fundamental. What that deeper structure might be is completely unknown. Some researchers focus on the holographic principle, which suggests that the information content of a three-dimensional region of space can be encoded on its two-dimensional surface boundary. This was proposed originally in the context of black holes, but has expanded into a broader framework suggesting that space itself might be emergent, built up from more fundamental information-theoretic relationships. In this view, space and time are like temperature. Temperature feels real and continuous. You can measure it precisely. But it's an emergent property that arises from the average behavior of billions of atoms. Space and time might be the same kind of thing, real and measurable at large scales, but assembled from something beneath them that doesn't look like space or time at all. The Planck length, in this picture, is the scale at which the emergent illusion breaks down, the point where the average stops working. The zoom level at which the hidden structure beneath becomes the dominant reality. None of these ideas have been experimentally confirmed. All of them are active areas of research. What makes the situation remarkable is that physicists are debating the nature of space, time, and the minimum structure of reality using mathematics alone, because the experiments needed to resolve the debate are beyond any conceivable near-term technology. The prize for solving this debate is enormous. A complete theory of quantum gravity would resolve every fundamental inconsistency in modern physics and likely reveal new physics we can't currently imagine. And the starting point, the clue hiding in plain sight, has been sitting in Planck's 1899 notebook all along. The Standard Model of particle physics is the most successful scientific theory ever built. It describes every known particle and every known force except gravity. It predicted the existence of particles before experiments found them. The Higgs boson, the particle that gives other particles their mass, was predicted by the Standard Model in 1964 and confirmed by experiment in 2012, almost 50 years later. The prediction matched the experimental measurement to extraordinary precision. The Standard Model is so accurate that physicists sometimes call it uncomfortably good. Uncomfortably, because it works far better than they feel they deserve given the known gaps in the theory. And it has gaps. Big ones. The Standard Model says nothing useful about gravity. It was built without gravity in it. Because gravity is so much weaker than the other forces at the scale of particles that ignoring it costs almost no accuracy. The error introduced by leaving gravity out of particle calculations is so tiny that no existing experiment could measure it. So it was left out, and the theory works, but leaving gravity out means the Standard Model cannot function at the Planck scale. At that depth, gravity becomes comparable in strength to the other forces. The assumption that justified ignoring gravity collapses completely. The equations, stripped of any gravitational terms, start generating answers that don't correspond to physical reality. There's a specific problem called the hierarchy problem. It asks why gravity is so much weaker than the other forces at the scales we normally work at. The answer might be that gravity's strength is diluted across extra dimensions, funneling most of its strength somewhere we can't detect. Or the answer might involve some new symmetry in physics that balances the forces differently at high energies. The Standard Model cannot tell you which, because it doesn't have the right machinery. Another gap. The Standard Model has no explanation for dark matter. Roughly 85% of all the matter in the universe produces gravity but emits no light. Galaxies rotate in ways that only make sense if enormous amounts of invisible matter surround them. The Standard Model contains no particle that matches the observed behavior of dark matter. Something is missing from the particle catalogue. A third gap, antimatter. The Standard Model predicts that matter and antimatter should have been produced in equal amounts at the Big Bang. Equal amounts would have annihilated each other completely, leaving a universe of pure energy and no matter at all. The universe clearly has matter in it. Something broke the symmetry. The Standard Model cannot explain what. Every one of these gaps points toward physics that exists beyond the Standard Model's reach. And every extension of the Standard Model that physicists have proposed, every new framework, every proposed new symmetry, eventually runs into the Planck scale as its limiting boundary. The Standard Model goes blind at Planck energies. Whatever the true theory of the universe looks like, it must describe physics that the Standard Model cannot. And it must do so in a regime where space, time, measurement and causality all simultaneously break down. Finding that theory would mean understanding the Planck length from the inside rather than pressing against it from the outside. So far, nobody has gotten through. The energy required to probe the Planck length isn't just extreme. It's extreme in a way that makes every other extreme in science look modest. Think about the most energetic things in the universe. A gamma-ray burst, the most powerful explosion known to astronomy, releases in a few seconds more energy than the Sun will emit in its entire 10 billion year lifetime. Cosmic rays, particles that arrive from deep space and slam into Earth's atmosphere, carry individual particle energies millions of times higher than anything the Large Hadron Collider can produce. These are the most energetic individual particles ever detected, and they arrive naturally from unknown sources across the cosmos. The energy required to reach the Planck scale is still vastly higher than all of that. Here's a comparison that makes it concrete. Take a large mountain. Not the tallest mountain on Earth, just a reasonably large one, the kind that covers many square miles of terrain and reaches several miles into the sky. That mountain contains an enormous amount of mass. Now use Einstein's mass-energy equation to convert every gram of that mountain into pure energy. Then compress all of that energy into a sphere the size of a single proton. That is approximately the energy density you need to probe the Planck length with a single particle. The mass of a mountain converted entirely to energy packed into a proton-sized space. No natural process humans have ever observed comes close to this. No device humans have ever built approaches it. The most powerful particle accelerators operate at energies roughly 1,000,000 billion times smaller than what the Planck scale requires. Even cosmic ray particles, the most energetic things naturally available, fall short by an enormous margin. The numbers are so extreme that physicists long ago stopped discussing direct Planck scale experiments as a matter of engineering challenge. It stopped being an engineering challenge. It became a statement about what's possible within this universe. There's a deeper point hiding in this calculation. The energy concentration required to probe the Planck length is, as established in earlier chapters, exactly the energy concentration needed to form a micro black hole at that scale. These are the same number. The observation energy and the collapse energy are identical, because both are determined by the Planck length itself. This isn't a coincidence. It's the universe announcing that the probe and the collapse are the same event. Attempting to look is the act of destroying. The experiment and its failure are physically identical. Some researchers have proposed looking for indirect signatures of the Planck scale rather than probing it directly. The idea is that if space has a minimum pixel size, light travelling across cosmic distances might arrive with tiny cumulative distortions caused by interacting with the granular structure of space-time along the way. Telescopes observing gamma-ray bursts from billions of light-years away have looked for exactly this kind of signal. The results have been mixed. Some observations set tight upper limits on how grainy space-time can be, ruling out certain models of quantum gravity. Others have found tentative hints of dispersion, meaning different frequencies of light arriving at slightly different times, which some versions of quantum foam predict. The signals are tiny, close to the limits of detector sensitivity, and the scientific community has not reached a consensus on what they mean. What they represent, at minimum, is the first serious attempt to find experimental fingerprints of the Planck scale without trying to reach it directly. Instead of climbing the wall, these experiments look for shadows the wall casts across the observable universe. Whether those shadows tell us anything definitive remains one of the most exciting open questions in modern physics. Imagine building a ruler capable of measuring 1 Planck length. Start with the material. At the scale of atomic structures, every physical object is held together by electromagnetic forces between electrons and atomic nuclei. Those forces operate at scales millions of times larger than the Planck length. Any ruler built from atoms has a granularity defined by the atoms themselves, which are already far too large to resolve Planck scale distances. You'd need a ruler made of something smaller than atoms, smaller than protons, smaller than quarks. Nothing we know of is smaller than quarks, except possibly the strings of string theory, which exist at the Planck scale and can't be assembled into a tool by any known means. But set aside material science. Imagine a theoretical ruler, something you've conjured mathematically rather than built physically. You extend it across a Planck length of space. What happens? The ruler has mass. Any physical object has mass. Mass, in Einstein's framework, curves space-time. At normal scales, the curvature caused by a ruler is so tiny it's utterly irrelevant. But at the Planck scale, the ruler's mass in a Planck-sized region of space pushes that region past the Schwarzschild threshold. The ruler's own gravitational weight causes it to collapse into a black hole before the measurement can be made. Every physical ruler long enough to span a Planck length, while being thin enough to fit within a Planck scale region, would collapse under its own gravitational energy. The act of existing at that scale is self-defeating. This thought experiment isn't hypothetical in the dismissive sense, it illustrates the real physics. Any physical system small enough and massive enough to interact with a Planck-length region of space would add sufficient energy or mass to that region to trigger gravitational collapse. The measurement device becomes the collapse. The observer becomes the event horizon. This leads to one of the most provocative statements in modern physics. At the Planck scale, the universe cannot be observed by anything made of matter, because everything made of matter has mass, and mass at that scale triggers collapse. The laws of physics appear to enforce a kind of absolute privacy for the Planck regime. Whatever is happening there, the universe will not allow matter-based observers to witness it directly. Whether some information theoretic observation, some description built from pure mathematical relationships rather than physical instruments, could circumvent this is what several theorists are now exploring. The holographic principle suggests that the information content of a Planck scale region is actually encoded on boundaries at larger scales. If that's true, you might decode Planck scale information by reading the code off larger surfaces rather than diving into the forbidden zone. But this would still be indirect. A map of the territory, not the territory itself. The universe has drawn a line. On one side is everything science can reach. On the other is the foundation of physical reality. The line is exactly 1 Planck length thick, and it has been enforced without exception at every point anyone has ever tried to cross it. What's on the other side has become the defining question of 21st century physics. Build the accelerator. Every last inch of it. Designing a particle accelerator to reach Planck energy using the same electromagnetic technology behind the Large Hadron Collider would require scaling up the machine by a factor so large that the math becomes almost meaningless. The Large Hadron Collider is 17 miles in circumference. A machine that reached even a small fraction of Planck energy using the same basic design would need to be so large that the only available location is open space. Physicists have worked through the numbers. A machine capable of probing the Planck scale directly would need a ring roughly the diameter of the entire Milky Way galaxy. 100,000 light-years of superconducting magnets. 100,000 light-years of vacuum tunneling. An energy supply drawing from something more powerful than any star. The Milky Way is about 100,000 light-years across. Light itself, moving at 186,000 miles per second, takes 100,000 years to cross it. Building a ring that large, using any conceivable engineering, would take millions of years at minimum. Travelling to place each component would require crossing distances that no human mission has ever approached. The nearest star to our Sun is over 4 light-years away, and we've sent no object that would arrive there in under tens of thousands of years at current speeds. The machine cannot be built. The statement isn't pessimistic about future engineering. It's a statement about physical scale. The gap between our current technology and the energy level required is so vast that it exceeds any reasonable extrapolation of technological progress, and yet, as established in the chapters above, the machine wouldn't even work. Reaching Planck energy means triggering Planck-scale black hole formation at the point of collision. The machine built across the galaxy would accelerate particles to unimaginable energy, smash them together, and the collision point would collapse into a microscopic black hole that evaporated before any detector registered anything useful. The machine fails by physical law, not by engineering limitation. This is one of the strangest situations in the history of science. Physicists can calculate exactly what the Planck scale looks like mathematically. They can write down the energy, the length, the time, the temperature. All the numbers are precise. What's forbidden is any experimental access to verify whether those calculations describe reality. It's like being able to calculate the exact address of a building you can never enter, in a city you can never visit, on a planet you can never reach. The address is precise. The destination is real. The path is permanently closed. This has forced physicists to develop a new approach, indirect inference. Instead of building the Milky Way machine, they look for effects that Planck-scale physics would leave on observable phenomena. Distortions in cosmic rays, anomalies in the cosmic microwave background, subtle corrections to quantum field theory calculations that might carry Planck-scale fingerprints. These indirect methods have produced suggestive hints and firm constraints, but nothing yet that counts as a confirmed discovery. The Planck scale guards its secrets aggressively, and the more physicists probe the edges, the more certain they become that what's hiding there isn't just a smaller version of the physics they already know. Gamma-ray bursts are the brightest events in the observable universe. In seconds, a single burst releases more energy than the Sun will produce over its entire existence. They're caused by the collapse of massive stars or the merger of dense stellar remnants. The light they emit travels across billions of light years before reaching Earth's telescopes. And physicists have realized those light beams carry something extraordinary. A potential message about the structure of space-time at the Planck scale. Here's the logic. If space has a minimum pixel size at the Planck length, then light propagating through space doesn't travel through a perfectly smooth medium. It interacts, in however subtle a way, with the granular structure beneath. Different frequencies of light would interact with this structure slightly differently, causing them to travel at slightly different speeds. Over billions of light years, even an incredibly tiny difference in speed adds up. High-energy photons might arrive at Earth fractions of a second before or after low-energy photons from the same explosion, even though they left the same source at the same instant. The time difference would be tiny, immeasurably tiny on any normal scale. But gamma-ray bursts produce photons across a wide range of energies simultaneously, and they travel for billions of years before arriving. The tiny speed difference accumulates over that vast travel time into a measurable delay. The Fermi Gamma-Ray Space Telescope, launched in 2008, was designed partly to look for exactly this kind of signal. In 2009, it recorded a gamma-ray burst from roughly 7 billion light-years away. Among the photons it detected, a high-energy photon arrived about 900 milliseconds after the lower-energy ones. 900 milliseconds is less than 1 second, but the journey was 7 billion light-years. Physicists ran the numbers. The delay was smaller than some models of quantum spacetime predicted, but larger than others. The result ruled out the simplest versions of quantum foam models, while leaving the more sophisticated versions untouched. It didn't confirm quantum gravity effects, but it constrained the possibilities. This is what Planck scale research looks like in practice. Not spectacular discoveries, careful, painstaking constraint of possibilities. Each observation rules out some models and narrows the space where the truth can hide. Other teams have looked at X-ray afterglows from distant gamma-ray bursts, searching for blurring of point sources that quantum foam would produce if light interacted with Planck-scale spacetime fluctuations. So far, those images appear too sharp to be consistent with the most dramatic versions of quantum foam. This pushed limits further. Every constraint is a piece of the puzzle. Every ruled-out model removes one wrong answer from the list. The universe is not giving its deeper secrets away easily, but it's giving hints. And each hint points toward the same conclusion. Whatever is happening at the Planck scale, it is stranger and more subtle than the most dramatic proposals anyone has made. The truth, when it comes, will likely be more surprising than any current theory predicts. The surprises may already be hiding in a concept so radical it suggests the universe is not a physical structure at all. In the 1970s, physicist Jacob Bekenstein made a discovery that seemed unrelated to the Planck scale, but turned out to be deeply connected. He was studying black holes. Specifically, he was trying to understand black hole entropy. Entropy, in simple terms, measures the number of possible internal arrangements of a system. A glass of water has high entropy because the water molecules inside can be arranged in countless different ways. A perfectly ordered crystal has low entropy because the atoms are locked into one specific arrangement. Bekenstein showed that the entropy of a black hole is proportional to the area of its event horizon, measured in units of the Planck length squared. Every Planck area patch of the event horizon corresponds to exactly one bit of information, a yes or no, a 1 or 0. The total information content of a black hole is the count of those Planck area patches. This was a stunning result. It meant that information in the universe has a maximum density. You cannot pack more than one bit of information into one Planck area of space. The Planck length isn't just a limit on distance, it's a limit on how much information any region of the universe can hold. Stephen Hawking built on this in 1974, showing that black holes slowly radiate energy and information through quantum effects. The two results together suggested something radical. The universe might fundamentally be an information system. Physical objects, space, time, particles, and forces might all be specific patterns in an underlying layer of pure information, the same way a video game's landscape is patterns in data. This idea, called the holographic principle, was developed rigorously in the 1990s by physicists Juan Maldacena, Gerard 't Hooft, and Leonard Susskind. The formal version says that the physics happening inside a three-dimensional region of space can be fully described by information encoded on its two-dimensional boundary surface. The three-dimensional interior is the projection. The two-dimensional boundary is the source. If this is correct, then the Planck length takes on a new meaning. The minimum pixel isn't a feature of three-dimensional space. It's a feature of the two-dimensional information sheet underlying space. Each bit of information on that sheet corresponds to one Planck area. Space itself is the readout of that information, projected outward. The implications are difficult to process fully. The chair you're sitting on, the air around you, the ground beneath the building you're in, these may be projections of information encoded on a surface you can't directly access. The three-dimensional world would be real, in the sense that all its properties and interactions are consistent and measurable. But the foundation beneath it would be information, not matter. Patterns, not substance. This is speculative. The holographic principle has been confirmed in specific mathematical contexts, but whether it applies to the universe we live in remains an open question. The observational tests needed to confirm it directly push against the same Planck scale limits discussed throughout this story. What makes the idea compelling is that it connects three apparently separate discoveries: Bekenstein's black hole entropy, the Planck scale information limit, and the breakdown of space and time at the Planck length. They all point at the same underlying conclusion. Whatever the universe is made of at its deepest level, it may be less like matter and more like math. The holographic principle sounds like science fiction, but it has a rigorous mathematical foundation, and the experiments designed to test it are among the most ambitious in modern science. The idea starts with a seemingly unrelated question about black holes. If you throw a book into a black hole, does the information in that book get destroyed? The laws of thermodynamics say information can never truly be destroyed, only scrambled. But a black hole swallows everything, including light, and appears to erase all details about what fell in. Only 3 properties of the swallowed object survive and become visible from outside: mass, electric charge, and rotation. Everything else, the words in the book, the arrangement of its atoms, the colour of its cover, disappears. Hawking initially argued that the information was indeed destroyed, which would violate thermodynamics. Bekenstein's entropy calculation suggested it was preserved on the event horizon. The debate lasted decades and became known as the black hole information paradox. Maldacenia's 1997 calculation changed the conversation. He showed in a specific mathematical universe that a quantum theory living on the boundary of a space is exactly equivalent to a gravitational theory living in the interior of that space. The boundary theory has no gravity. The interior theory has full gravity. Yet both describe identical physics. Every event in the interior corresponds to a mathematical state on the boundary, and vice versa, with perfect one-to-one correspondence. This is called the anti-de Sitter conformal field theory correspondence, or the ADS-CFT correspondence. It's the most cited paper in all of physics. In the mathematical universe where it was derived, the holographic principle is exact and proven. The catch is that the mathematical universe in Maldacenia's calculation has a specific geometry, a universe with negative curvature, like the interior of an infinite saddle shape. The universe we actually live in has a slight positive curvature, more like the surface of a sphere. The ADS-CFT correspondence hasn't been proven to work in our actual universe's geometry. Extending it there is one of the major ongoing projects in theoretical physics. If it does extend, the consequences follow naturally. Our universe's 3-dimensional interior is the projection of information encoded on its 2-dimensional boundary. The Planck length is the minimum cell size of that boundary grid. Physical reality, everything we see and measure, is the readout. Some researchers have run with this and proposed experimental tests. If the universe is a hologram, the projection from the 2-dimensional boundary into 3 dimensions should introduce a tiny amount of noise into measurements of 3-dimensional space. 2 positions in 3-dimensional space that are different might correspond to the same cell on the 2-dimensional boundary, producing a fundamental fuzziness in position measurements larger than the Planck length, but smaller than anything currently detected. A detector called the holometer, built at Fermilab in Illinois, ran from 2012 to 2016 specifically to look for this holographic noise. It used 2 interferometers separated by a short distance, measuring their relative positions with extreme precision. The experiment found no signal, ruling out the specific version of holographic noise it was designed to detect. But ruling out one version of the hologram isn't ruling out the hologram itself. Different models of the holographic principle predict different types of noise with different properties. The holometer ruled out one prediction, narrowed the space of possibilities, and the search continues. The universe, as always, is being careful about what it reveals. Stephen Hawking changed his mind. Twice, in 1974, Hawking showed that black holes are not completely black. They slowly emit radiation through a quantum mechanical process near the event horizon. This radiation, now called Hawking radiation, carries energy away from the black hole. Over an incredibly long time, far longer than the current age of the universe for any black hole of significant size, the black hole shrinks and eventually evaporates completely. The problem: Hawking radiation appears to be purely thermal. Thermal means random, like heat. A thermal signal carries no information about what created it. If a black hole evaporates into purely thermal radiation, all the information about everything that ever fell into it is gone forever. Hawking initially argued this was correct. Information gets destroyed. Thermodynamics has an exception for black holes. Most physicists were deeply uncomfortable with this conclusion. Quantum mechanics, the most precisely tested theory in science, is built on the principle that information is conserved. Physical laws run equally well forward and backward in time at the quantum level, which requires information to be preserved. Allowing black holes to destroy information would require rewriting quantum mechanics at a fundamental level. The tension sharpened into a crisis called the black hole information paradox, and it became one of the most contested problems in theoretical physics for decades. Eventually, Hawking changed his mind. By the early 2000s, motivated partly by the holographic principle and partly by new calculations, he conceded that information probably escapes from black holes in a scrambled form encoded in the correlations within the Hawking radiation. The radiation looks thermal when you examine individual photons, but the whole collection of photons emitted over the lifetime of the black hole contains hidden correlations that encode the original information in a deeply scrambled way. The mechanism by which this happens at the Planck scale remains unsolved. The debate now centres on how information gets out. The answers proposed involve physics directly at the event horizon at scales near the Planck length. One proposal, called the firewall paradox, suggests that the event horizon is not the calm, empty crossing point that general relativity predicts. Instead, quantum effects create a wall of intense radiation at the horizon, burning anything that crosses it and imprinting the information on the emitted radiation. This would violate one of general relativity's core predictions, that crossing an event horizon feels like nothing special from the falling observer's perspective. Another proposal involves what physicists call the ER equals EPA conjecture. ER refers to Einstein-Rosen bridges, another name for wormholes. EPA refers to Einstein-Podolsky-Rosen entanglement, the quantum phenomenon where two particles share a connection regardless of distance. The conjecture says these two phenomena are the same thing. Every pair of entangled particles is connected by a microscopic wormhole at the Planck scale. Information travels between entangled particles through this tiny geometric bridge. If true, the fabric of space-time at the Planck level is threaded with a web of entanglement-generated wormholes, connecting every entangled particle in the universe through Planck-scale tunnels. The quantum connections between particles would be literally geometric, woven into the structure of space itself. This idea sits at the absolute frontier of physics in 2026. It hasn't been proven, but it connects black hole physics, quantum entanglement, wormhole geometry, and the Planck scale into a single picture in a way that many researchers find deeply suggestive. The answer to the information paradox may be written in the geometry of space at the smallest possible scale. Two particles, opposite sides of the galaxy. Measure one, and the other responds instantly. Quantum entanglement is one of the most tested and confirmed phenomena in all of science. Two particles, created together or made to interact, can share a quantum state. Measure a property of one, such as its spin direction, and the other particle's spin is instantly determined, regardless of the distance between them. Einstein called this spooky action at a distance, and he found it deeply troubling. He hoped it would turn out to be explainable by hidden information carried within the particles themselves. Experiments in the 1980s, building on work by physicist John Bell, showed conclusively that Einstein was wrong. The correlations between entangled particles are stronger than any hidden information model can produce. The connection is genuinely non-local. The two particles share information in a way that doesn't travel through the space between them. For decades, entanglement was treated as a strange quantum feature with no connection to the geometry of space-time. Then came the ER equals EPRA conjecture, proposed by physicists Juan Maldacena and Leonard Susskind in 2013. suggesting that the geometric wormholes of general relativity and the quantum connections of entanglement are the same underlying phenomenon viewed from different perspectives. In this picture, every pair of entangled particles is connected by a microscopic wormhole. The wormhole doesn't allow travel because it's far too small and unstable for anything to pass through, but it provides a geometric link in spacetime that corresponds exactly to the quantum entanglement connection. If this is right, entanglement isn't a mysterious non-local connection layered on top of space. Entanglement is the thing that builds space. The network of entanglement between quantum fields could be what weaves spacetime together. Space between two objects exists because of the quantum entanglement connecting the underlying fields. Regions with strong entanglement are nearby in space. Regions with weak entanglement are far apart. This is the it from qubit idea, championed by physicist John Wheeler in his later years. The universe is built from information. Physical space and geometry emerge from the patterns of quantum information. The smooth spacetime of general relativity is a large-scale approximation of an underlying information structure. At the Planck scale, where that information structure is most visible, space stops looking smooth. The individual threads of the entanglement network become distinct. The geometry loses its familiar properties. The quantum foam Wheeler described in 1955 might be exactly what an entanglement network looks like up close, a chaotic tangle of connections that averages into smooth space from far away. This framework, still in active development, potentially answers several open questions simultaneously. It explains why entanglement appears non-local, the connection doesn't travel through space because it's part of what creates space. It explains why spacetime is smooth at large scales, quantum entanglement in stable matter creates stable, smooth geometry. It explains why the Planck length is a limit. Below the minimum entanglement cell size, there's no geometry at all, just the raw information layer. Nothing here is confirmed. The mathematics is promising and the conceptual picture is attractive, but experimental tests remain extraordinarily difficult. Yet the direction feels right to many researchers. The universe's deepest secrets seem to involve not particles, not waves, not fields, but the quantum relationships between things, the connections, not the objects. And those connections exist at every scale, all the way down to the Planck length, which appears to be where the connections themselves begin. The Big Bang is the standard story of how the universe began, an unimaginably hot, dense point that expanded into everything we see. The evidence for it is overwhelming. The cosmic microwave background radiation, the proportions of light elements in the universe, the observed expansion of space in every direction. But the standard Big Bang model has a problem at its very centre. When you run the equations backward in time, every measure of density and temperature increases without limit. The universe gets hotter and denser as you approach the moment of origin, and at the very first instant, all the equations produce infinities. The model breaks down. Physicists call this the initial singularity, a point of infinite density, infinite temperature, and zero volume. Every physical law fails there. General relativity predicts the singularity exists, but cannot describe what it is or what came before it. Loop quantum gravity offers a different answer. Because loop quantum gravity describes space as a discrete network of Planck-sized loops, it has a natural mechanism that prevents singularities. In the standard model, as the universe shrinks towards zero, density increases without bound. In loop quantum gravity, as the universe shrinks, it eventually reaches a state where the loop network is maximally compressed. The loops can't get smaller than 1 Planck length. Density reaches an extreme but finite value, then a repulsive quantum force, a consequence of the discrete geometry, pushes back. Instead of collapsing to a singularity and stopping, the universe bounces. This is the Big Bounce. Before the Big Bang, there was a previous universe. It contracted, reached maximum density at the Planck scale, and the quantum geometry pushed back hard enough to reverse the collapse into an expansion. The expansion we see today as the Big Bang is actually the rebound from a previous collapse. Time existed before the Big Bang. Our universe's beginning was a transformation, not a creation from nothing. This doesn't mean the previous universe was like ours. The bounce erases most of the detailed structure of the contracting universe. What survives is primarily a nearly uniform dense state from which a new universe springs. Some researchers have proposed that certain large-scale patterns from the previous universe might survive the bounce and appear as subtle signals in the cosmic microwave background radiation. Groups studying that radiation have looked for exactly such signals. Some claimed hints have been found. A pattern called the power deficit at large scales, where the cosmic microwave background has slightly less variation at very large angular separations than standard models predict, matches some big bounce predictions. Other researchers argue this could be a statistical artifact. The question of whether the universe bounced at the Planck scale remains open. But the existence of a serious, mathematically consistent model in which the universe has no true beginning, only an endless cycle of collapse and expansion, fundamentally changes the oldest question humans have ever asked. Where did everything come from? The answer loop quantum gravity offers is that it came from a previous version of everything, stretching back into an infinite past at the Planck scale. That answer may never be confirmed or ruled out, but the question deserves the best theories physics can produce. If space is made of discrete Planck-sized pixels and time ticks in Planck-sized steps, then the universe is fundamentally a finite state machine. A finite state machine is a system with a specific, countable number of possible configurations. At any given moment, the universe occupies one of its possible states. One Planck time later, it occupies another state, determined by the rules of physics applied to the previous state. This description sounds exactly like a computer simulation. Each Planck time is a clock cycle. Each Planck-sized region of space is a memory cell. The laws of physics are the program. The universe runs the simulation forward, one tick at a time, and what we experience as reality is the output. Physicists are careful about how far to push this analogy. It doesn't necessarily mean the universe is running inside someone else's computer. It means the universe has properties structurally similar to a computational process. Whether that similarity is deep or superficial is an open question. But the philosophical implications run immediately into a very personal question: free will. Every thought you have, every decision you make, every action you take is the result of physical processes in your brain. Those processes are made of atoms. Atoms obey physical laws. If the universe is a deterministic finite state machine running on a Planck-scale grid, then the physical processes in your brain are determined by the state of the universe one Planck time before, which was determined by the state before that, stretching back to the Big Bounce or wherever the chain begins. Quantum mechanics introduces genuine randomness at the subatomic level, which breaks pure determinism. Your decisions may involve quantum random events, but randomness isn't freedom. A dice roll isn't a choice. The pixelated universe, if real, frames free will as a macroscopic experience generated by a system that, at its deepest level, is computing its next state from its previous one. What you experience as choosing is what the computation looks like from inside. This isn't a new philosophical problem. Determinism versus free will has been debated for centuries. But the Planck scale picture of a discrete, finite state universe puts the question in its starkest form. The minimum step size of the universe's clock is one Planck time. Between ticks, no events occur. The universe simply occupies its current state, waiting for the next computation to complete. Whether consciousness can exist within that framework in a way that produces genuine agency, or whether agency is always an emergent illusion from within a computation, is a question physics cannot currently answer. It sits at the intersection of quantum mechanics, neuroscience, and philosophy. What physics does offer is the following: the minimum building blocks of time and space are Planck-sized. Everything we experience, every thought, every perception, every action, is assembled from those building blocks in ways we haven't fully mapped. The gap between a Planck tick and a human thought is roughly 43 orders of magnitude. The story of how the universe gets from one to the other is still being written. The Standard Model leaves too many questions unanswered to be the final theory. 26 free parameters, meaning 26 numbers that must be measured and plugged into the model by hand, because the theory cannot predict them from first principles. The mass of the electron, the strength of the electromagnetic force, the exact mixing angles between quark types, all of them must be put into the equations from the outside. A truly fundamental theory should derive these numbers from deeper principles, not accept them as unexplained inputs. Then there's dark energy. The expansion of the universe is accelerating. Something is pushing space apart at a rate that increases over time. The Standard Model has no candidate for what this something is. The leading theoretical explanation, quantum field theory's prediction of the energy of empty space, gets the answer wrong by 120 orders of magnitude. That's a number followed by 120 zeros. Some physicists call this the worst prediction in the history of science. Beyond the Standard Model, three major directions of research compete. Supersymmetry proposes that every particle in the Standard Model has a heavier partner particle differing in a property called spin. The electron's partner is the selectron. The quark's partner is the squark. Supersymmetry would resolve the hierarchy problem, stabilize the Higgs boson's mass, and provide a candidate for dark matter. The Large Hadron Collider has been searching for supersymmetric particles for over a decade. It has found nothing. The simplest versions of supersymmetry are now ruled out. More complex versions are still theoretically possible. Extra dimensions, proposed by various models, suggest that gravity leaks into dimensions beyond the three we experience, which is why it appears so much weaker than the other forces. If gravity spreads out across extra dimensions, its apparent weakness in our 3 dimensions is just a dilution effect. Experiments at the Large Hadron Collider have looked for signs of extra dimensions through microscopic black hole formation and unusual scattering patterns in collisions. No confirmed signals have emerged. Composite Higgs models suggest the Higgs boson itself is made of smaller constituents bound together by a new strong force. This would explain the hierarchy problem through a different mechanism. Experimental signatures predicted by these models haven't shown up clearly in data yet either. Every one of these frameworks eventually runs into the Planck scale as a boundary condition. Whatever theory replaces the Standard Model must reduce to the Standard Model at energies below the Planck scale and must match smoothly onto quantum gravity above it. The Planck length is the seam where all beyond Standard Model physics must eventually connect to the deepest theory of space and time. Finding that seam from below using particle physics experiments and finding it from above using quantum gravity theory, and having both approaches arrive at the same answer would be one of the greatest achievements in human intellectual history. The seam has been located. The two sides haven't yet been matched. The work continues every day in accelerator halls and on chalkboards in university offices around the world. The universe has been running its own experiments for 13.8 billion years. It has generated events far more energetic than anything humans can produce. Neutron stars have merged, releasing gravitational waves and gamma-ray bursts. Black holes have collided, sending ripples through space-time itself. Cosmic ray particles have been accelerated by unknown mechanisms to energies millions of times beyond the Large Hadron Collider's reach. And all of it has left traces that travel across the universe and arrive, eventually, at Earth. Gravitational wave detectors, specifically the Laser Interferometer Gravitational Wave Observatory, first detected the ripples of space-time distortion from 2 merging black holes in 2015. Since then, dozens of events have been recorded. Gravitational waves pass through space at the speed of light, and if space-time has a discrete structure at the Planck scale, that structure might modify how gravitational waves propagate over cosmic distances. Some researchers have proposed that a discrete spacetime would cause high-frequency gravitational waves to travel slightly faster or slower than low-frequency ones, a phenomenon called dispersion. Current gravitational wave detectors are not sensitive enough to measure this effect at the level quantum gravity theories predict. Future detectors, including a proposed space-based observatory called the Laser Interferometer Space Antenna planned for the 2030s, would be orders of magnitude more sensitive and might detect such effects. Cosmic ray observatories have detected particles arriving from beyond the galaxy with energies so extreme they challenge existing physics. These particles, likely protons or heavier nuclei accelerated by violent cosmic events, hit Earth's atmosphere and produce cascading showers of secondary particles that ground-based detectors measure. The energy distribution of these particles carries information about the physics that accelerated them and about how particles at those energies interact with the quantum vacuum of space during their billion-year journeys. Several experimental groups have found tentative evidence for unexpected features in the highest energy cosmic ray spectrum, features that some quantum gravity models predict would appear as signatures of Planck-scale spacetime effects on particle propagation. The statistical significance of these signals is debated. More data from next-generation observatories should either confirm or rule out these interpretations within the next decade. The cosmic microwave background radiation, the faint thermal glow filling all of space as a remnant of the hot early universe, also carries potential signals. During the first fraction of a second after the Big Bang, the universe passed through energy scales that approached the Planck energy. Quantum gravity effects during this period would have imprinted subtle patterns on the distribution of that radiation. Specific predictions from loop quantum gravity, string theory, and other frameworks differ in their predicted patterns, and detailed maps of the cosmic microwave background from current and future telescopes offer the best available window into that Planck scale era. The universe is generous with clues. Reading them requires instruments of extraordinary sensitivity and theoretical frameworks precise enough to know what signal to search for. Both are advancing rapidly. The closest humanity has ever come to seeing Planck-scale physics wasn't in a laboratory. It was in the sky. Science moves by falsification. You build a theory, derive a prediction, run an experiment, and see whether reality matches the prediction. If it does, the theory survives. If it doesn't, you revise. The Planck scale has introduced something science wasn't built to handle, a regime where predictions can be derived but cannot be tested directly, where the experimental tools needed to falsify a theory are physically impossible to build, and where the closest available tests are so indirect that multiple competing theories can fit the same data. This has generated a serious debate about the nature of scientific knowledge itself. Some physicists argue that string theory, despite its mathematical beauty, has failed the basic test of science by producing no falsifiable predictions accessible to current or foreseeable experiments. They argue that a theory which cannot be wrong is not a scientific theory. Karl Popper's principle of falsifiability, which has guided scientific practice for nearly a century, would classify string theory as metaphysics under this reading. String theorists respond that the same charge could historically have been levelled at general relativity in its early years. Einstein's theory made predictions that required measuring the bending of starlight during a solar eclipse, an experiment that seemed practically impossible before Arthur Eddington carried it out in 1919. The tools to test a theory sometimes take decades to develop. The mathematical consistency of string theory is itself evidence, not proof, but evidence. Others argue that consistency should not be mistaken for truth. The theory of a flat Earth is internally consistent. Mathematics has consistent theories that describe things which don't exist. Internal consistency is necessary, but not sufficient. The silence of the Planck scale, its total resistance to direct experimental access, has forced a philosophical reckoning. Physics may need to expand its definition of what counts as confirmation. Indirect signatures, mathematical consistency, connections to other confirmed theories, predictive success in adjacent regimes, these may need to carry more evidential weight when direct access is physically impossible. This isn't comfortable for a discipline built on hands-on experiment, but discomfort doesn't make the reasoning wrong. What the silence also tells us is important. Every measurement that fails to find quantum gravity effects sets a tighter constraint on the properties those effects can have. Every ruled-out model removes one possible description of Planck scale reality from the list. The silence is not empty. It contains the shapes of all the things that aren't true, and the shapes of things that aren't true are part of closing in on what is. The scientific community hasn't given up. It has adapted. New tools, new indirect methods, new theoretical connections are being developed constantly. The problem of quantum gravity has attracted some of the most creative minds in science for decades, and sometimes the most transformative discoveries come right after the period of deepest uncertainty. Quantum mechanics itself emerged from exactly such a period, when classical physics had run into walls it couldn't explain, when the equations were producing nonsense, when the assumptions everyone had worked with for centuries were quietly breaking down. The Planck scale may be the same kind of invitation. A wall that isn't an ending, but a door. Every civilization that ever looked up at the sky eventually asked the same question. What is everything made of? The ancient Greeks proposed atoms, indivisible particles, the bottom layer of matter. For 2,000 years, atoms were philosophical speculation. Then chemistry proved they were real. Then particle physics cracked them open and found protons and neutrons inside. Then a deeper level of quarks and gluons inside those. Each time physicists found a bottom floor, a deeper basement revealed itself beneath. The Planck length may be where that staircase ends. At every previous level, scientists could eventually build tools to explore the new layer. The atom was invisible to naked eyes, but yielded to chemistry. Atomic nuclei were invisible to chemists, but yielded to particle accelerators. Quarks were invisible to early accelerators, but yielded to more powerful ones. The pattern has been consistent for over a century: patience, better tools, deeper access. The Planck scale breaks that pattern for reasons that are, for the first time, fundamental rather than technological. The barrier isn't a matter of building a stronger accelerator. The barrier is woven into the relationship between measurement, energy, mass, and space-time geometry. Every tool you could conceive of fails for the same reasons, at the same scale, governed by the same physical laws. This means either one of two things. The first possibility, the Planck length is genuinely the bottom floor. Space has a minimum pixel. Time has a minimum tick. Information has a maximum density. The universe is built from irreducible units at this scale, and what those units are, whether strings, loops, information bits, or something unnamed, is what physicists are working to determine. Below this floor, there is nothing. The question of what's smaller has no answer, because smaller doesn't exist. The second possibility, the Planck scale, is the limit of our current framework, not the limit of reality. There is something below the Planck length, but our mathematics, built from calculus and quantum fields and general relativity, cannot describe it. The breakdown of our equations at this scale tells us about the equations, not necessarily about the universe. A future theory might see through this barrier the way Einstein's theory of general relativity saw through limitations that had stopped Newton's gravity. Physicists argue intensely about which possibility is correct. What they agree on is that the Planck scale is the most important address in all of physics. Every unsolved problem connects to it. Dark matter, dark energy, the origin of the universe, the nature of time, the unification of forces, every deepest question leads, eventually, back to this length. Max Planck found this number in 1899 while trying to fix an equation about light bulbs. He couldn't have imagined that his footnote would become the central mystery of the 21st century. You are alive at a moment in history when the most fundamental questions about the nature of reality are openly unsolved, When the best minds in science are debating whether space is continuous or pixelated, whether time had a beginning, whether information is the deepest substance in the universe, whether the smooth world you experience every day is a projection from a layer of reality too small to ever touch. That uncertainty is the most exciting thing about the universe. The door at the bottom of everything is locked. The key hasn't been found yet, and the scientists working on it believe, with good reason, that behind it sits the most profound truth the human mind has ever tried to reach. The search isn't over, it's just getting started.